Okay, so today we're going to be talking about carboxylic acids and their and their derivatives. Okay. So to get a carboxylic acid, you need the carboxylic acid derivative, and it needs to undergo hydrolysis with either an H plus or an OH group. So we can just write that down just for general information. Also, we can write carboxylic acid derivatives as CAD. So CAD undergoes hydrolysis with either an H plus or an OH group, which will then give us carboxylic acid, or Ca. So we're going to look at a couple of them now. So if you started, let's say, with an ester, and you reacted, hydrolysis with H plus, and then you have H2O, then you'll get your carboxylic acid with an OH ethyl there. Well, what if we started with acid chloride instead, and same thing, an H plus with H2O, acid chloride, we get the exact same thing, but instead of this, we're gonna get an HCl. Okay, what about if we use a nitro? Reacting it with the same thing, want it to go under hydrolysis. Except this time, what if we choose an OH group? We'd get, if you guessed it right, the same thing, but an NH3 byproduct. We could keep going with, let's say, an acid anhydride. And we reacted that with an H plus, H2O. You get two equivalents of the carboxylic acid. And for an amide, and we reacted, let's say, an OH group this time with water, we get a carboxylic acid with NH3. So if you look at these two, they give you the exact same thing, both with the byproducts, and all the other ones have the exact same product, so major product. So just to keep that in mind. And then we're going to go over one type of carboxylic acid reaction, like the Fischer esterification reaction. Okay, I want to write this. Okay, so let's say we had this, and we wanted to react it with an OH with the methyl and an H2SO4. Then we'd get the ring, but this oxygen is going to be attached to the methyl group instead. So now we can go over the mechanism. But first we have to react the OH with the methyl with the H2SO4. So the lone pairs on the oxygen are going to attack this hydrogen, and then this bond is going to go back to the oxygen. And then that'll give us the methyl, and this oxygen now has 2 hydrogens with it, so now it's positive. And if we react it with this, which I'm just going to write as R instead of continuing drawing the aromatic ring, with that, the oxygen here, because it still has lone pairs, are going to attack the hydrogen, and then this bond is going to go back to the oxygen, which will give us, remember I'm writing the R for the group, for the ring, and then the oxygen is still positive because it still has a lot. And if we react that with the HO with the methyl, this oxygen is going to want to attack here, and then this double bond is going to get broken to a single bond to give us methyl. There's an H here. This is still positive. We have an OH group here, the R group, and another OH. Because you remember this is the HO with methyl, is this right here. Okay, and then when we react it with an acid, the acid is going to attack this hydrogen here, and then this bond is going to go back to the oxygen, giving us the oxygen with the methyl, again the OH, because the only thing that left, we remember, is a hydrogen. Then we have another OH here, and then our R group never leaves, and then that acid comes back, and now this oxygen, because it still has lone pairs, is going to attack the hydrogen, and then that bond is going to go back to the acid. We're going to get sorry, an OH here. We're going to O with 2 hydrogens this time, so it's going to be positive in our group, in our O methyl. And sorry, I keep moving it, if that makes sense, because this is the methyl up here, now it's down here. Doesn't really matter, because you're just rotating it. And then it's an ugly arrow. These oxygen's lone pairs are going to go here to create a double bond, and then this, because the carbon is like, oh no, this is too much, is going to go back, so then water leaves. Giving us our group, and then the oxygen attached to that methyl still, and then we have this double OH bond, so the oxygen is still positive. And then we're going to react that with the acid that was right here, that left. So the acid is going to attach to this hydrogen. Then this hydrogen bond is going to go back to the oxygen to give us our final product of the ring with the oxygen and the methyl and the O bond. And then what's left over is a byproduct of H2O. So we could just add the H2O here. And then that's Fischer esterification. And then we can do a small reaction wheel as well. I don't know, reaction wheel. But it's not a big one. Okay, so let's say we started with this acid chloride. And we wanted to make this ester. What would we use to create that? You can say an OH with a methyl group, which will give you an ester. But let's say we wanted to do an amide. What would we use for that? Probably an R group and an NH2. So we'll get rid of this chloride, put in this, and an oxygen, a hydrogen is going to attack the chloride, and it'll become HCl. Okay, what about making an anhydride? Making an anhydride. We'd use, because you're adding another group to it, you'll do an ester. Okay, and let's say, what if we wanted to start with an acid chloride? A carboxylic acid. And wanted to go to the ester. We'd first have to react it with SOCl2 to give us the acid chloride. And then from there, we do the exact same thing we did here. So we'll add in the OH group with the methyl. And then we're also going to look at another reaction of a carboxylic acid and, something else, I guess. This is another reaction. So let's say we started with something that looked like this. It's not really pretty. And we reacted it with the acid anhydride and heat. What would we get? So let's try to figure this out, by looking at the mechanism. Once again, start with your starting material. And we had this as one of our reagents. Okay, so this O, has lone pairs. So then they're gonna attack this carbon. So then this is all happening at the exact same time. So the double bond's gonna break and it's gonna go back to this oxygen. But then this oxygen is like, actually, no. So they're gonna give it back. And then this bond here, that one right there, is gonna go all the way over here to this carbon. What does that look like? It looks like this. And there's also a hydrogen here, and because the oxygen, it has so much on it, is gonna have a positive charge. And then when we react it with this, because that's what left, this part, this oxygen's lone pairs are going to attack that one. And then that bond is going to go back to the oxygen, giving us that. I would just like to do a good, just point something out, that this right here, okay, that's a weird sheet they gave me, is a good leaving group. So this oxygen's lone pairs, this one, is going to attack this carbon. And then once again, we're doing the same circle. Two double bonds get separated, double bonds come back. This bond right here is gonna go over here, in which they leave, right? And then that'll give us, do we still have, oh yeah, we do. A ring, actually. It's ugly. And there's the double bond oxygen there. There's a positive because there's, once again, too many things for the oxygen to handle. And then we have this group here, and react it. And then these, my goodness, these lone pairs are going to attack this hydrogen, and then this bond is going to go back to that oxygen to give us the final product. Of that. Then that's the end of this video for week 6, carboxylic acids and their derivatives.